I'm Bryce Moore.
I'm Justin Dix.
And our advisor is Dr. Doom. So our project is to design, build, and fly a plane that will meet competition standards, as well as attract future students to join/create an AIAA chapter here at South Dakota State. With our projects, we have 3 flight missions and 1 ground mission. The first flight mission is crew only. It is the pilot and co-pilot in the cockpit, and you fly just around the track. The second mission is with the crew members, like before, EMTs, a patient on a gurney, and a medical supply cabinet, which is what the payload is going to be located in. And that is what your scoring is based off of. That is the amount of weight you're carrying, as well as nothing is touching during that flight. The third mission is just like a commercial flight where you have passengers in your fuselage integrated on how many passengers you hold. And then your ground mission is how efficient you can switch between different missions, as well as getting out park configuration. Now, with the park configuration, our plan is to fit within a 2.5-foot parking space. However, the maximum wingspan is 5 feet, so you have to design a wing that can fold up and fit inside that parking space.
So a couple goals for our project. We want to build a plane that'll fly for more than 5 minutes. So roughly the mission time is going to be 5 minutes, and there's 3 of them. So we want the plane to fly more than 5 minutes. We want to carry a payload of roughly 5 pounds. That will be our cabinet. We also want our plane to take off within 20 feet. We want to record a flight lap time of 1.5 minutes, and then we want to compete in the competition and place top 2/3. So some of our stretch goals: we want to carry a payload of 10 or more pounds, take off in less than 10 feet, and then record a flight lap time of about 1 minute. And then we would like to place top 30.
Some of the similar work that's been done with this is one is NASA. They do research and training for it. So at the bottom right, you'll see NASA utilized the 3/8 scale F-15 to launch, and it was remotely controlled, and it was used to record stick, and that way it took the pilots out of it and created less risk for that. Another one would be the National Weather Services for weather data collection. The military uses drones, and then obvious.
So there are many decisions that go along with our plane. The first one is the empennage, which is essentially the tail of the plane. So we chose 3 tails: the conventional, the T-tail, and then the cruciform tail. And based on our cost, manufacturability, sustainability, and weight ratings, we found that the conventional tail was the best suited for our practice.
So with airplanes, there's 3 positions where a wing can usually be on a plane: a high wing, the mid wing, and then a low wing. So we had to look at whether our payload would be integrated around the wing, the stability of the plane during flight, and how easy it is to manufacture. With this plane being a cargo plane, we're going to be flying at relatively low speeds, so we want to have good stability in those low speeds. So the top wing performed the best in that aspect, as well as with it being on top, we can completely avoid our payload, which is going to be on the bottom and the middle of our plane. So that's overall why we went with the high wing design.
So out of many of the airfoils in the world, we chose these 3: the Clark Y, the NACA 2412, and then the NACA 0015. So with the cost, manufacturability, they're going to be roughly the same with little differences. But the biggest thing and why we chose our airfoils were all the alpha, the coefficient lift versus alpha data. And with all these alpha, which is the angle of attack, which is essentially how far your airfoil is pitched up, all of these data is based on 0 angle of attack. And with that, we chose the Clark Y as our airfoil.
So our next item would be what battery to choose to run our servo and our receivers. So on here we have the 1450 milliamp hour and the 2200 milliamp hour. And then we have the rating broke out down below. And then based off of the criteria, it turned out that 22 kilowatt hour would be the best. Then on this, so our servos, depending on the surface area of actual aerions, perhaps brighter elevators, determine the required torque for the servo itself. So with aerions being the highest, and then the flaps being the middle. With the first servo right there, you're going to see that one we chose for aerions because that one had a higher voltage, has a higher torque rate. The middle one would be the middle range. So that would be our flaps. That one has like middle range of torque, and then the smaller one would be the ones who run our rudders and flaps. Rudders and motors.
So with choosing our motor, there are many different motors. For this spec sheet specifically, these are all the high-end motors that are roughly going to be from 10-pound planes to upwards to 42 pounds. So there's also regulations for battery size for our competition. So all these batteries over here are pretty much gone because they require 33 to 44 volts for the battery size. And so the first three are roughly what our battery is going to be like. And so right now our plane's sitting roughly at 13 pounds. So the highlighted motor is suggested for a 14.5-pound plane, which will definitely suit our needs. And then with the 18 to 22 voltage battery range, which is good for our regulations. So the propulsion battery regulations include the 100 watt hours, so it cannot exceed 100 watt hours. And the max current that it can receive is 100 amps, or the maximum it can exceed is 100 amps. And so with all these different batteries out there, I've come to the conclusion that this 22 volt, 3200 milliamp hours, and then 30 C rating. With all these calculations, we get a max amperage of 96, which is under our 100 amps, and then our watt hours is at 71, which is under our 100 watt hours.
So with everything we've talked about, we've had a design around all of our needs. So as you can see, I talked about earlier how we can fold up the wing. So the wings in our current model have hinges. They'll have latches at the bottom to hold it in place. The nose will be 3D printed, which will store the motor that Bryce just got done talking about, as well as the crew members, since they're supposed to be elevated above the motor. Inside the fuselage, we will have a rail system that'll make it easy to load and unload the different missions. And then our tail is our conventional tail, is modeled with NACA 0015 airfoils. Very symmetric, very thin, perfect for stability. So this is the weight breakdown currently of our plane. As you can see, the tail is the heaviest part. This is because we're using a PVC pipe, a square PVC pipe to make the tail in so it's easy to connect the airfoils in the back as well as run wires through it. That might be something we need to look at to reduce the weight since we want the center of gravity to be more towards the front end of the plane. However, to help counteract the center of gravity, all the electronics are placed on the front side of the plane. With that being 25% of the weight, you're starting to shift your CG back. And then the fuselage, currently, we have no weight reduction. You can easily make weight reduction by making cutouts while keeping structural integrity. So this is the foldable wing. So the total length when it's down has to be under 60 inches or 5 feet. When you fold it up, it has to fit between 30 inches or 2.5 feet. So based off what we have right now, we are well within the range in both categories. So we will pass the needs of competition. So with our wings, we need to take off. We need to take off within 20 feet. So this first graph is our force of lift in pounds per velocity. And so this is without flaps. And so we want our plane, after everything's said and done, it's gonna be around 20 pounds. So we have this horizontal line showing where the plane needs to be and where the graphs intersect is the speed it could be at. So without flaps, our plane's sitting about 3 to 6 degrees, which is what it's gonna be on the ground. We're looking close to 20 meters per second and 15 meters per second, which is around 44 and 32 miles per hour, which is pretty hard to do in that 20-foot takeoff. Now, if you add flaps, you're actually adding 0.6 to your coefficient of lift. And in the equation down there, you can see that if you increase your coefficient of lift, your force of lift will increase without velocity changing. So you can take off in a faster, you can take off with more weight in a slower speed, which that second graph shows. We actually can take off within 12 to 15 meters per second, which is around 28 to 32 miles per hour. So we think that we can achieve that with our current motor within 20 feet, so we can take off. So with our foldable wings, we had some initial testing done, testing the different latches and how they would hold our wings together.
So how we tested the wings was we took 2x4, we cut it into two 18-inch sections, and then a middle 24-inch section. We connected the hinges to the top of the ends of the 2x4, and then, like previously showed on the slide before, the hinges from the bottom side. And then what we did was we took an initial height measurement and we started adding weight in increments of 10. Then every increment, so a deflection, a new height deflection measurement. So we got up to 50 pounds. This one is the gold latches at full weight at 50 pounds. But this one is the silver latches.
So these are our results from the initial testing. As you can see, the silver latch did deform the least at 0.625 inches, and the gold latch deflected at about an inch. So now with these latches, they do come with some safety concerns. Since the gold latch does not have any locking mechanism, was really concerning because when we lifted the weight, when we went with our testing, we lifted the weight up. The apparatus actually came undone because the gold latch was not locked. So the silver latch, luckily, did do the best, and it had the best locking mechanism. So that's what we're choosing.
So on the Gantt chart right now, we are currently at the design phase. We're still doing some simulations. We've done already. In the future, we're going to be ordering material and electronics and then start manufacturing.
So this is just a little overview of our budget, about how much the aircraft's going to cost, as well as transferring the team of 6 to competition. There'll be 6 of us, 3 of us, our advisor, and then 2 classmen. It's a cost breakdown itemized. So our upfront costs for electronics are pretty high. We're just starting off, so we have to bring those materials in, but you can use that year after year. So that price will decrease each year. Building the plane itself, we have a nice we're adding a little bit of leeway just in case we have catastrophic failure during testing. We want to have that extra budget just in case something bad happens, but we don't plan to use the whole 2,000. And then you're 4,000 for travel, so that's why our final price is around 8. Questions?
So this thing's like what, 5 feet wide and how long?
So it's 5 feet wide, and then right now we're looking also around 5 feet long. 5 feet long, very close. Yeah.
I don't know if this is a factor that you have to consider, but what's the worst conditions that your plane take? I don't know if they say on competition day, just assume ideal conditions, for wind or turbulence.
Yeah. So for us, we want to, we're going to assume ideal conditions. Even planes of this size, when you're flying, if there's any weather, you're going to experience a lot of issues. So for us, we're experiencing ideal conditions. When we're testing it, obviously we're in South Dakota winters always not that great.
Mm-hmm.
So come testing time, we'll figure out what type of weather conditions are
You guys have a plan for like how to get younger students involved in this club? Like obviously you want it to become something like Baja or Formula SAE. Do you guys have a plan of how to get interest for this kind of thing?
Yeah, so currently we have 200 classmen. One in specific I've been in really close contact with, talking about design. He's all about it. He loves the design aspect of it. So just kind of getting them like, hey, like this we need to think about. I had a meeting with him. He had a model, and I told him, I was like, all right, that's a good model, but we have to manufacture this. And so teaching the process of you have to build a plane that not only you can manufacture, but will perform to competition standards. So just kind of keeping them in the loop on how all that is done is pretty important. So I think they'll learn and come years from now when they're in our position, they'll be very successful.
I also think us building the plane will help, because like, you know, you'll have these like designs like, oh, this may or may not happen, but we're gonna actually have a plan and they can go and look, okay, there's actually something here, not just like the concept. So hopefully that will attract people and word by mouth too from the younger class.
What about the stability? Have you checked the stability? Is it natural stable or is it control system?
So are you talking about in the air or the structural
Because the air,
in the air?
where you fly,
So-
be stable, is that right?
Yes.
How you can achieve this stability?
So that's with our wide wings that we have going on. So essentially the wide wings and the airfoil will help us with the takeoff, and then the wing position, since the center of gravity is lower than the actual wing, will have it won't like top heavy, and so with the force of the air acting on the wings as it flies through the air, it'll act kind of as like a balance essentially.
Also, the Clark Fly airfoil is a very stable airfoil, especially at low speeds. You actually see a lot in RC models, and Clark Fly is actually the most used in RC applications. Simply for the fact that RC planes don't fly as fast, and that Clark Fly has a very low coefficient drag while maintaining a high coefficient lift. So that's creating a very stable plane in those low speed conditions. So that's why we chose the Clark Fly airfoils for that reason.
Do you guys have a plan for serviceability? Like RC planes crash, so like, are your parts, are you gonna have like replaceable parts, or is it total?
Yeah, so the way I have it modeled right now is each piece you'll be able to pull apart, and then you might have to re-glue or re-nail something together. And that's with our increased budget, is like if you have that catastrophic failure, they're very easily manufactured parts. So it could be a quick, like, all right, we have to rebuild this. It would only have to take a day or so to do a rebuild process, just for the manufacturing side of this.
I'd have some concerns with the hinge coming up done during flight. Is there adding any other latches or
So in that, we're gonna have a design so we can't flex downward, it's flexing upwards. In our test, we're hitting the ends of our wings. In reality, you're not going to have it's not gonna be fixed on one end. It'll have that give come up. If you watch planes fly, like wings have quite a bit of give in the first place. So I'm not overly concerned with it. I think as long as we latch, it stays latched, and nothing catastrophic happens, I think the plane will still fly.
On slide 6, just had a question for your, what was your decision for payload integration? Like, what was your thought process behind choosing like the high between the mid and low? I just want.
Okay, so with our I-wing, everything is we connect on the top side. And so right now it's 8 inches tall. Our little figures are going to be 3.5 inches tall, which are going to sit on the bottom side of the plane. So we know a mid-wing, you're gonna have that connecting point, and if you have to go straight to the middle of the plane, you're going straight to your payload. So you have to integrate around that. And if you have a bottom wing, yes, you can build on top of that, but then it really increases the height of your center of gravity. So it's gonna be on the top side, so you're gonna be not as stable as those are being on the bottom side, which is also why the I-wing is super nice.
Thank you.
So are you guys like aiming to actually test with like the actual payloads or like weights of like cots and like loading systems and medical devices, or are you guys really just like building it and then testing that and then moving forward into that stage? Or like, what are you guys just building a smaller version or the full size version?
We'll build the full version. We'll build like the inserts, we'll do inserts, test program.
More questions?
Have you done anything with the center of gravity? Do you know where that's at?
Yeah, so currently without payload in it, our CD is about an inch behind where our wing ends. And when you add the extra weight of our payload, especially that other supply cabinet, you scoot towards the front, your CD is gonna shift directly below the wings where you want it.
Do you have the option of moving around your payloads, different types of payloads?
Yes, they,
Get your center of gravity wherever you want.
you can kind of see here, so the EMT, so the patient's 5.5 inches, so our medical supply cabinet, based off what they're saying, I don't recall this exactly, how that, like, I know you have to have your EMT next to your patient, but I think you might be able to move around with your medical supply cabinet based off what the rules of brand, I don't know if that's a fixed thing.
Yeah, so what we did was we just modeled pretty much that template, so if we need to move it out further.
If we're truly having issues with the center of gravity, was our model willing to go back a little bit farther to match the CG?
All right, any other questions for this team? If not, good job.